Hello. You guys there?
Yeah.
I did some investigating with the Mandelbrot, not with Mandelbrot, but with the circuitry. It looks like the explanation we're looking for is in calculus and electrical engineering. It's a little bit above, you know, what we're doing with it. I don't know what you guys found, if you found anything. Oh, thank you. While you guys are waiting, where would a point be at 1 plus I?
Like that's not in like an imaginary plane or whatever.
On that imaginary plane that's on the screen. Where is 1 plus I? It said in that example that it's not
1, 1.
It's at 1, 1, right?
Uh,
It would be where 1, 1 would be if it wasn't imaginary.
wait, I think.
Right?
Yeah.
It would be 1 to the right plus 1 along the I direction. So
Yeah.
it would be like 1, 1. Notice
Yeah.
1, 1 is not in the black region. I was talking to Mr. Knaus, by the way. You don't call it range. We said that it has a limited range because I is not, don't get confused. That is not, we were thinking about it in order to think about where that was, we treated it like a y-axis, but it is not actually a y-axis. So that's not the range. So it's important to notice everything in the black region is a complex value. All right. So Mr. Knaus said you can have an x imaginary. You can have an imaginary axis just for the y-axis in terms of y, and same for the z. Okay, so it doesn't exist in some place. All right, it's imaginary. We express it on a plane visually, and you can't get confused that, so it's not on the y-axis. Okay, it's somewhere else perpendicular to the x-axis. So that imaginary and that real are perpendicular, but it doesn't mean that it's an x and a y. So that's not the same as a domain and a range. So I had to correct that. Oh, actually, I'm going to bump you guys to the next warm-up. All right. Parallel circuits.
Oh yeah.
Read that. Those are instructions at the top. And then you're just following the formula. When I looked this up on YouTube yesterday, there's a lot of calculus involved. It's not difficult calculus. It's stuff that you're going to get to with Mr. Knaus in a couple years. All right. Or maybe not next year, but the year after. And then the year after that. So you will get to it, you know, taking derivatives of logarithmic functions and things like that. You know, and so they have Ohm's law that you're going to learn, right? And so that's all going to be covered. So this is kind of like a prerequisite preview is all you're going to get from this. So in Algebra 2, they give this to you in simple form. You see that what is Z again? It's impedance, isn't it?
I mean, it looks like it.
But you have different impedances if you go along a different pathway. So they just separate it into Z1, impedance 1 and impedance 2. And the way to find overall impedance there is that formula that they're giving you. It's the product over the sum, it looks like.
So you take the impedance of one like part, and then you pick the product of that, and then
And you call it Z1.
I think it's easy enough.
Yeah, I mean, it looks scary, but it's actually easy enough, like you said. So, I mean, the imaginary parts of this, why they're complex, what I gathered from my investigation was that the complex numbers allow you to avoid having to do complicated trigonometry with sines and cosines, because these follow sine. They called it a sinusoid on Khan Academy. They called these sinusoids. They follow sine and cosine wave patterns. The frequency, it's based on frequency and wavelength. Mr. Knaus said that these capacitors is what Zig was saying. They're building up. They're building up the voltage, I guess, that's coming through. There's two things. There's voltage and current that are coming through. And I think Ohm's law says that voltage over current is used with the I is the resistance. I believe that's what it is. Resistance is equal to voltage over current. So as current and voltage go through and they go into a capacitor, the capacitor starts to store it until in an alternating current, it then switches directions and then I think it clears it out. The inductor is the inverse of the capacitor. So it does the inverse. And I don't know what I don't know electrical engineering. So you will have to go through, you will learn about that later on, okay, as it reverses flow. But let's talk about as it's going into the capacitor and then as it comes out of the capacitor. If you have low frequency waves, big wavelength, versus high frequency waves, and these are sinusoids because they follow the sine. You are going to graph sine and cosine, and they're going to look like this. Oh, you guys aren't on my screen. Okay. Well, if you have a capacitor here and a capacitor here, what happens is the high frequency waves, they happen, and I hope I don't reverse this, they happen quickly. The frequency is high. So as the frequency is high, the energy is not getting, it's either getting stored more in the high frequency or less. I think Mr. Knaus said that the lower frequency ones, because they come in slower, it gives the capacitor more time to build up energy or build up the current or build up the voltage. Okay, and I'm kind of chopping this up, so I know I am. And then the high frequency ones, because of the frequency, it doesn't give the capacitor enough time to build that charge up, to build up charge. So these equations are based on the frequency. So later on, you're going to get different kinds of measurements of frequency, and I believe they called it, what's the one? It's omega, omega, and that's going to have to do with angles based on the rotations of these things. You know how we said multiplying by I, you get these rotations, right? Where you have I and you have negative I, and then you have the real, right? And the not real and multiplying. So you get these trigonometric rotations here with the degree measures. And then also you have, let's say you have a real component and then you have an imaginary component, right? Remember our vectors? And then the resultant vectors like that. This angle is going to affect, I believe, it might affect the frequency, which affects all of this stuff. So you can see that there's so much more to this that we're not going to be discussing, all right? But that the imaginary numbers help us to do this without having to do these calculations with sine and cosine functions. The eyes, what we're doing allows us to skip through that. And then it also, I saw, it makes the derivative process much simpler when you're doing the calculus with this, which if you're an electrical engineer, you're going to be using calculus with this to actually do these problems. Yes. I think electrical engineers make a lot, by the way.
So resistance is just a resistor, and then the inductor is negative.
And inductance and capacitance are inverses of each other.
Is inductance or capacitance negative?
Capacitance is negative.
Okay.
Daniel, can you turn off your video?
So if you look on this complex plane, I think you have like resistance is on the real, right? So you have resistance on the real. You have inductance up here, which we say is L, so it's Li, right? This is imaginary. And capacitance is the inverse of that. So it's negative Ci. Notice that inductance is on the imaginary axis, and so is capacitance, right? It's on the opposite side. Resistance is right in the middle. All of these lend to impedance. All right, so I don't want to go over this so much when I don't have enough information for you. It's because there's so much calculus involved in this that we don't have the prerequisites to go much further. Okay, in a parallel circuit, there is more than one pathway through which the current can flow. To find the impedance Z of a parallel circuit with two pathways, first calculate the impedance Z1 and Z2 of the pathways separately. So here, let's get.
We can't see the.
Yeah, I'm gonna draw it. So we have this first one has a resistor, 4 ohms, followed by an inductor. Oops. And then that's a pathway. And that has 5 ohms. Okay. Then there's another alternate pathway that comes down here with a resistor and a capacitor. The capacitor has 3 ohms. And this resistor has 7 ohms. This is the Z2. This will be the Z1 pathway. The formula for impedance, Z, is going to be the product of the pathways over the sum of the pathways. And maybe you'll remember that when you do electrical circuits in calculus or in your physics class. Okay, so this might be familiar to you when you get to it. Okay, so then we write this out. Resistors are real, so that's 4. Okay. Inductors are positive imaginary, so this is 5I. And so that is your impedance Z1. It's actually not too bad. If you follow, the current follows this pathway, and then it alternates through, right? Then you are going to get 7 minus, because it's a capacitor is the inverse of a of an inductor. Okay, so that's going to be minus 3I. So then we're going to just plug it into the formula to get the impedance for the parallel circuit. Okay, so here we go. So I have the product. I kind of like this. This is kind of fun. Over the sum. Any questions so far? Okay, and then here you're going to have, let's see, 28. You're going to have negative 12I and positive 35I. So negative 12I, positive 35I. Now watch this. Some of you are still having trouble with this here. The I times the I is just going to make it negative after. It's going to multiply by -1 to whatever I get from these coefficients. So 5 times negative 3 is negative 15 times -1 is positive 15. Okay? I'm going to simplify that first. 28 and 15 is 43 plus 23I. Okay? Over, now the denominator. 4 plus 7 is 11. And then it'll be plus 2I. And then you don't leave it like that. What do we do with that? We multiply by the complex conjugate, right? On top and bottom. Yes or no? Did you guys leave your answer like that?
Yes.
But didn't we
Yeah.
Multiply by the conjugate.
multiply by the complex conjugate
Multiply by 11
Yeah, we
minus 2.
on both top and bottom, which means you're really multiplying by 1. Okay, so now here we go again. Seems like a lot of work. Okay, 43 times 11 is 473. Okay, and then I have negative 86I plus, and then 23 times that is 253I. And then it's going to be plus, because it's negative, and then I times I is I squared is negative, so positive 46. Okay, and then let's see what that comes out to. We get, I think I only want to do one of these, just because we have other stuff we have to do, and we're running low on time on the school year. So we'll just do this one. Okay, so we have 519. And then this will be what, 253 minus 86. See, 167. So that's going to be plus 167I. Now the denominator here, it's going to be a squared plus b squared, I remember. So it's going to be 121 plus 4 is 125. And then you write it as a real part, 59. Oops, I'm running low here. Oh, by the way, the 6th grader said it's better if there's no glare and it's a darker room. You guys tell me. Is that better? That should have.
Yeah, that's better.
It's darker room, but there's no glare now. Okay, or much less glare. Okay, so
It looks like you're telling ghost stories.
Yeah, it looks like you are.
Ooh, okay, so I have this over that, plus I have I. Now, if you think about that, where is that on the complex plane? If this is imaginary and this is real, and going up is inductance, right? Which is L, I'll call it L. Okay, L. And going down on the imaginary is capacitance. And then you have your real. Well, here's your real amount of resistance, right?
Around like 4-ish. Is that like 4?
Okay, yeah, let's do an estimate. Yeah, just a little bit more than 4 along the real. 1, 2, 3, 4, and a little bit more, right? So you have this vector that comes out to there in the real direction, right? And then what is this here? That's like 1, here, I'll tell you what it is. 167 divided by,
It's like 1.3.
167 divided by 125. Yeah, it's like 1.3 I. So 1, 2. So if I'm here and then I'm going to only go up about 1.3, then look at what the result is. The absolute value is what we're finding. That's what this is. Up at the top, it's the overall impedance is going to be this value here. All right? If you wanted to get the absolute value of that. But so this explains it one way as some real and some imaginary in a complex plane. And that's going to be the impedance. And later on, this angle here is going to matter. I know it's kind of small, but this angle here that it makes is going to matter. But you guys you're equipped now with what we did on vectors. And now what you're seeing here, when they talk about that, you're ready to start talking about that angle and what it does. And then your mind can be blown. Right now, your mind might not be quite blown because we didn't make it all the way to using it. But that's what makes it so exciting to advance through Science Academy, is that by the end, you guys are going to be, hopefully you're going to be loving this stuff, and that's careers for you. And imagine getting into a career you love and you get to do this and people want to pay you a lot of money to do this. It's going to be great. I'm just telling you. But hey, don't give up when you run into a problem. If, yesterday we talked about that. A student said, is this going to be on the when I hear that, that's a red flag. No, that's where you double down. You go in and you be aggressive and you ask questions. Okay.
Mr. Rosenthal.
Yeah.
So on Desmos, I graphed 6 points: AB, BC, AC, BA, CB, and CA.
All right.
I put sliders for A, B, and C, and then I hit play. And they're just moving like a squadron of points.
Okay.
And moving back to the center to intersect, and then
can you show me? I'll let you share during office hours. Can you share it during office hours?
Okay.
Okay. Snapple fact, by the way, bubble wrap was originally invented as a wallpaper in 1957.
Yeah, it was invented as a wallpaper yeah.
Weird.
It was invented as a textured wallpaper.
Yeah, that's so strange. All right, so then we had some other Mandelbrot, but we're getting time. We have to move on. So sorry. Oh no, that was the same one, I think. Oh no, that was called a Julia set.
This is a Julia set.
It's a whole you can look it up. We don't have time. We have to get back to what we were doing. It's been a while since we've been away from parabolas for a while now. So let's get back. Let's see what you guys remember about completing the square. Solve that quadratic by finding square roots. So see if you can do that right now. See if you can solve that one, not by using the quadratic formula. Do not use the quadratic formula. Use by finding square roots is how they want you to do it. It did not say complete the square, by the way. You will not need to complete the square here.
Oh, okay.
What do you notice about the trinomial on the left? Is the first term a perfect square?
Yeah.
Is the last term a perfect square?
Yeah.
Yeah.
The middle term
It's 2AB, but it's negative.
double the product of the square roots.
Yeah.
Yes.
Yep. This is one of the normal squares.
Okay, everybody, take a look. Okay. The square root of this is x. The square root of that is 4. So it's 4x. And 8x is double that. Okay, and those are perfect squares. So we now know the shortcut to factoring this is that this is a perfect square. This whole thing is a perfect square trinomial. It comes from x, and because this is minus, it's x minus 4 squared. Question?
How do we How do we know this is a perfect
Which means
trinomial?
x minus 4 makes it equal
We had
5.
we had a lesson where we tried to identify special polynomials. One of the special polynomials was a difference of squares. The other kind was a perfect square trinomial. We
So x is,
identified it by saying, oh, is the first term a perfect square? Yes. Is the last term a perfect square? Yes. Then we check the middle term to see if it's double the product of the square roots. Square root of that is x. Square root of that is 4. So 4x is the product of the square roots. And the middle term is double that. Okay?
but it's negative.
And it's minus. So that if this was plus, then this would be x plus 4. If that's minus, then it's x minus 4.
Does this mean that x is either 9 or negative 1 because...
Wait, hold on.
25.
Now, Daniel, you could just factor normally and get that. But eventually, you're going to realize when that's a perfect square, it's x minus 4 times x minus 4.
Okay.
Okay? All right, David, you were saying?
Would this mean that x is either 9 or negative 1 because the square root of 25 is plus or minus 5?
That x is... Oh, wait, hold on one sec. So now, once you get it, I want to make sure everybody understands how to get to this part. Because this is what we need for the next example. You need to know how to get to... Once you get this, you need to understand that this is your goal, to get it to look like this. When you get it to look like this, you take the square root of this and the square root of this. And what is the answer to the square root of x minus 4 quantity squared? What is the answer to that?
X minus 4? The absolute value of x minus 4.
Absolute value of x minus 4. Okay? On this side, it's 5. Now,
Plus or minus 5.
some of you skip, what is it?
Plus or minus 5 after you did the absolute value.
Not at this stage. If you skip this step, then you can go right to this step.
I don't bother with the absolute value.
Okay? Now, I know Mr. Knaus didn't do this step. He skipped right to this step. Okay, but this is actually what that is. Okay, and then add 4. So it's 4 plus 5 and 4 minus 5. Okay, so we're solving using a different method now, using square roots.
This is fun too.
Mm-hmm.
Oh, Mr. Rosenthal, why do we keep the 25 on that side instead of making the equation equal to 0?
You're going to see. I don't know if I want to give away where this is going. I'm teaching you how to do something. I wonder if anybody's on to it already. Why would I be showing you this when we already have more than enough ways of doing this? Why teach you this way when we already know the quadratic formula and we already know how to do it by factoring, and that covers all situations?
Completing the square?
Well, completing the square is how we get the quadratic formula. So that's the end result of that is the quadratic formula. But don't try to be the one to guess what this is for. It's going to happen soon. Okay. Share. Okay, perfect squares. In example 1, the trinomial x squared minus 8x plus 16 is a perfect square trinomial because it equals x minus 4 times x minus 4. Sometimes you need to add a term to an expression, x squared plus bx, to make it a square. So they don't all come in squares, but you can add something to it to make anything a square. This process is called completing the square. There we go. Oh, and they have all this diagram stuff. I don't think I'm into that. I'm going to skip the diagram. Okay?
I think
But what I will do to supplement,
I think that's how Mr. Knaus would. I think that's how Mr. Knaus would have done it. Isn't that how he did it?
I'm not a fan. Now, if you want, the lesson's there for you. You can go back and do the diagram stuff. But here's what I'm going to show you. How did we get a perfect square trinomial? We had an a squared x squared. So this was a perfect square. Plus bx plus a perfect square over here. And the b was made of 2ac. Remember? The square root of this was ax. The square root of this is c, and then double that, 2acx, okay? That's what we said makes a perfect square trinomial, all right? So how do I get, let's say that I have x squared in an equation. Let's say I have 3x squared, and that's not a perfect square. If I divide both sides of my equation by 3, right, whatever that is over here, let's call that some d, okay? What I can do is I can get rid of that, and guess what? Now it's a 1x squared. And I divide everything by 3, by the way. Whatever I divide by, I have to divide everything by 3. Okay, so I can always manipulate that to get that to be a perfect square, and I can get that to be 1 if I need it to be. All right? If I get that to be 1, then I have to worry about the last one being a perfect square. If it's not a perfect square, that c squared, get rid of it, subtract it, and move it over here. Whatever this is, let's say it's just c. Get rid of it, move it over, subtract it on both sides. Now, I'm going to plug in a new one. I get to add whatever I want into this empty space. I want to add something, call it e. I want to add a square that also adds up to the middle term. Something times itself, and it has to be something plus itself. Well, something plus itself means that I just divide this by 2. Okay, if I divide this by 2, this would be AC plus AC is 2AC. AC times AC, so this would be AC squared over here. Now all of a sudden I am able to manipulate and create a perfect square so that I can factor it the way that we did the last problem, and then whatever junk that I have over here, I can take the square root of both sides and I can get either an irrational answer here or I can get a rational answer. So I know that that was kind of abstract. So let's actually do that. No. Oh, yes. Okay, so find the value of c that makes this a perfect square trinomial. Then write the expression as the square of a binomial. Try that. That's kind of an intermediary step. They're not throwing you right into the deep end on that. They're asking you to just find out what c would have to be so that that would become a perfect square trinomial. X squared is already a perfect square. You know c needs to be a perfect square. But which perfect square? Well, you know that that 16 there has to be made up of 2 times the product of the square roots of the first and third term.
This is completing the square, right?
Yeah, it's completing the square. And you guys probably remember how to do this, some of you.
I kind of forgot.
Okay, you know when we factor, right? It's what is the product of 2 things that add up to the middle term, right?
Yeah.
If it's a perfect square, then it's got to be a number and itself, right?
Wait, I remember when I was completing the square, we had this like other formula that you like plug b into.
We're gonna get to that. We're gonna get to that.
Okay.
But I just want conceptually to look. What number has to be the same as itself that adds up to 16?
8.
This is 8 plus 8, right? Which would mean that this has to be 8 times 8. If you have to use these numbers in here, it's got to be the same numbers that you use. Then this has to be 8 times 8. So I know C has to be 64. Now look at it. This is 1x squared. The square root of that is 1x. The square root of that is 8. And then you double that, and you get your 16x. And that's because doubling is meaning 8x plus 8x, right? Okay, you see that?
Okay.
All right. And so then if you think about it, x plus 8 times x plus 8. Watch the distributive property. X times x, x squared. X times 8 is your first 8x. 8 times x is your second one. They're the same because these are the same. And then look, 8 times 8 have to give you that 64. So the numbers that you're using to double up here, so how would you work this backwards? Now we get to the formula. You take this and divide it into 2 equal parts, 8 and 8. Then square that and get your C. So what is this term? That's the B term. Whatever B is, even if it's not a perfect square, you can still do this. Whatever B is, divided by 2, and it could get ugly. It could be an odd number. Okay? All right? But if it's an even number, then, you won't have to work with, halves or anything like that. Then what I'm going to do is, once I divide that by 2, what did I do with the 8? I squared it. So you square this. What is this squared? B over 2 times B over 2 is B squared over 4. So this term is always going to be or B over 2 squared. And the way you find it is you cut this middle term in half and square it, and that's what goes there. Now, if I have an equation and I add this to one side of the equal sign, you better be adding it to the other side.
What if A is more than 1?
We divide it out of the problem.
Oh, that's mean to A.
Yeah, I know.
That's a cruel and unusual punishment.
Okay, any questions about this? So you cut that 16 in half, you get 8, and then you square it, and that's it. That C is 64. Cut it in half and square. They use this to say, oh, okay, x squared. I got to cut the 16 into 2, so it gives me 8 here. So put an 8 and an 8 there. And then you get these combinations. You get x times 8 is 8x, and then this x times this 8 is 8x. And then you finish the box. But that's the same thing that we did algebraically without the picture.
I think that's how Mr. Knaus taught us, Mr. Rosenthal.
Yeah. It's just, to me, it's a lot of time for something that you guys already get for the most part. I mean, it might be helpful for some students. Okay, solving equations. The method of completing the square can be used to solve any quadratic equation. When you complete a square as part of solving an equation, you must add the same number to both sides of the equation. Okay, go ahead and try this one. Do not use the quadratic formula.
Now we know that when you get a squared minus b squared, it's
I did mess up my entire
a minus b, a plus b. And if it's a squared plus b squared, it's a plus bi, a minus bi.
Yep, you sure do. It's the sum of squares is
Has to be a
yeah, it has complex factoring.
Mr. Rosenthal, it's adding b squared over 4 to both sides, right?
Uh-huh.
I might have missed part of it.
It is. Check to see if it's a perfect square trinomial first. Okay, so the square root of this is x.
It's not.
The square root of that is 2, and then double that. 4x, you look here, that's not 4x, it's 12. Okay, so therefore it's not. So this shouldn't be a 4 here. So one, if you're having trouble with what to do right now, one thing you can do, there's another way to do it, but this is a nice algorithmic way to do it. Subtract 4 on both sides. Now you have a free space and you can add whatever you want to both sides of the equation as long as you do it on both sides. Gee, what should I add? Cut the 12 in
Maybe
half.
36.
Cut the 12 in half, which is 6, and square it. So I'm going to add 36 to both sides. Number one error students make, write this in your notes so that when you get this on your test, you have a little note to self. Oh, don't forget to add it on both sides. Students forget to add it on this side. They say, oh, let me just make this a perfect square. They add 36 and do nothing over here. You can't just add 36 to an equation.
It's like, I didn't change the value at all.
Yeah, if you change the value on a scale, on a balance scale, you will visually see it get heavier or lighter. Okay, but because you don't look at a scale, you forget. You have to account for it.
Wait, Mr. Rosenthal, how did you make the 436?
I didn't make the 436. I subtracted this 4 on both sides. I got rid of the 4, and it showed up over here. Okay? Then I had emptiness. And then I did what I said. I said, cut that in half. Daniel, what's half of 12?
6.
And then square it.
36.
So this is 6. This is minus 6 minus 6, and this is minus 6 times minus 6.
So we need to fill out the perfect square trinomial.
Yeah, and then you have to do it on the other side. Whatever you add to one side, you add on the other. Now I've constructed a perfect square, which I now know because that's minus. Whatever you split that into, it was 6 and 6. Okay, whatever you split that into, and that minus sign, it's x minus 6 squared is equal to 32. Okay. Now, the other way I could have done it is to not subtract 4. I could have figured that I needed a 6 and a 6, so it's 36. And I could have thought, well, what do I need to add to my 4 to get to 36? Oh, if I add 32 to that, I'll get 36. Then I would add 32 on both sides, and I would go to that. That's another way to do it. But it's usually algorithmically, we get rid of the C value by subtracting it or adding it if it's a negative. Okay? And then you just do this. Now that's the absolute value, but we'll skip and we'll say that this is plus or minus. Let's see, what is that? 4 times, that's 4 times 8. No, it's 4 root 2. And then you have to add your 6. There you go. I'll take questions now. Still have not revealed why we're learning this new method or another method. It's not new, you did it in algebra. No questions, okay.
Wait. Okay, never mind.
Okay, never mind. Okay, try that one. Now look at their A is not 1, A is 2. So see if you can deal with it now. Can you create a perfect square on the left-hand side and get all the rest of the junk in your way, that's in your way, to the right-hand side? It's not junk, by the way. One person's junk, right?
It's junk.
One person's trash is another man's treasure.
Yes. We are the music makers, and we are the dreamers of the dreams. Roald Dahl, Willy Wonka, Charlie and the Chocolate Factory.
Oh, Mr. Rosenthal, when you previously referenced the solving method, did you say that the central term had to equal both of the coefficients multiplied by each other? The coefficient of the x without the power, the coefficient of x to the first, would it be
It'd be 2 times the square root of this coefficient and this coefficient. Or
You
not.
get an imaginary number.
Hopefully the first thing everybody did was divide everything by 2.
Yeah, don't you get an imaginary
But
number
those
because you have to
there
subtract
are
3?
I don't know. I haven't done the problem yet.
Yes, you do.
The next thing I want to do is I want to get rid of the 7 because that's not going to help me get my perfect square. So I'm going to have I'll take questions going along. Just stop me or else I'm going to keep going. Okay.
Oh, keep going.
I'm going to divide this. So, sir, and instead of calling this b squared over 4, I think it's easier to cut it in half and square it. It's commutative.
Much easier.
It works. It works both ways, but I think it's easier to cut this in half, get 2, and then square it, and add that to both sides.
-3.
Okay, don't shout answers, please. Okay, now this is 2 plus 2, and this is 2 times 2. So it's x plus 2 squared. Okay. Square root of both sides, and you're going to get
Yay, I.
Plus or minus.
that's right, because I didn't. If I put absolute value, no plus or minus. If I don't put the absolute value, you need to have the plus or minus.
And -2.
And then yes, and then finally, I'll just go the same color. I don't think anybody's going to say, how did you get from purple to purple? But they might. And now we kind of understand this answer in the complex plane. We could actually calculate the impedance here. This is one way to represent an impedance. Negative resistance. Any questions? Wow, you guys must be getting it, or you just don't like to talk and out yourself. You don't want anybody to know. Too blurry to see numbers. When was that? That was at 8:39. Okay, that was before. Hopefully you can see now. That was at 8:48. It says we can't see too high up. Okay. All right, so we're good, I think, in the chat. Okay, standardized test question. The area of the rectangle shown is 72 square units. What is the value of x? Go for it. Try to use our new method of doing it. Don't use the older methods, use this new method. I'll use whatever method I want, Mr. Rosenthal. Don't tell me. Hopefully you've set it up like this. Length times width is the given area 72. I'm going to leave a gap. I think all of these are divisible by 3. They are. I'm going to divide everything by 3. Give me 1 second.
You mentioned there was like some sort of formula we can use to find the missing c.
Yeah, it's b over 2 squared.
Okay, thank you.
Yeah,
Wait, b over. You mean
b over 2
b over
quantity squared.
what? Wait.
You cut this. I'll do it right now because I'm going to complete the square right here. So
Okay.
here's b is 2. So 2 divided by 2 is 1, squared is 1.
So b over b squared.
It's b over 2. It's b is 2. B over 2 quantity squared. This.
Oh yeah, that was what it is. I remember.
Yeah, that's what you add to both sides. Now this is x plus 1 squared is 25. Oh, that came out nicely. And if it comes out nicely, it means that you could have done it a traditional way and it would have worked out nicely the other way. Okay, square root gives you plus or minus 5. And then x is equal to negative 1 plus 5 is 4 and negative 6. Questions about that one? Oh, no, one more step. Because this is an area problem, it can't
So
be.
you eliminate the negative.
Yeah, the answer is only 4. Be careful when it applies to a real problem. You have to be careful with what your solutions can actually be. Mathematically, you can get things that you can't get in the real world. Questions about this? So we're completing the square. Why are we doing this? Anybody? Don't look it up or anything.
To derive the quadratic equation.
No, which we can do.
Formula.
Okay, yes or no, does anybody need to practice completing the square more before we go on?
Yes, I would like to.
Okay, then
Not really.
I'm gonna go, let's do one more.
Okay.
Let's do number 11, everybody.
Yay, sounds cool.
6x squared plus 48x equals 12. Well, I don't want 6 to go into it nicely. Hold on, I want a number where it doesn't go in that nicely. I think I'm gonna make my own. Oh, maybe
No, Mr. Rosenthal, what's the problem with number 11?
it's too easy.
11's good. Number 11's good. It's fine.
It's too easy. Everybody stop doing number 11. I'm gonna make one myself.
Warning, crazy fractions ahead. Mr. Rosenthal is making up a problem.
Solve by completing the square.
It's not nice, Mr. Rosenthal.
Yeah, but you need practice with this because I don't think they gave you good practice because they're going to give you all those examples where the common factor divided out everything every time, and then they're going to give you problems in the homework set or on a test where it doesn't happen that way, and then it'll be out of left field, and I don't want that. Okay, I'm going to start doing it step by step. First, divide everything by 3.
What?
Ugly fractions.
No.
And again, you know, fractions, people say, well, I don't get what you're doing now. It's all because I added fractions. I'm not going to do anything different. If you're having trouble with it now, all of a sudden, it could be because you're just not strong with fractions, which is very common.
Fractions, smactions.
Okay.
I can deal with it a little bit.
You could see why I got that orange step.
Actually, these are nice fractions. I mean, they're annoying, but easier to work with.
At least it's
Now what
not
I'm
like
going to do is I'm going to
27
show
over
you
64.
what this is. So if I take half of this, it's 4/6. 4/6 and 4/6 is 8/6. 8/6 is 4/3. So this is half of that, if you're paying attention. Okay, I'm going to make that 2/3. Now I'm going to square it. That's what goes there. 4/9 on both sides.
These are actually pretty easy to do.
Okay, now, do I have to figure out again what it factors into? No. It's whatever half of this was. Half of it.
2/3.
All right, David, don't shout it out. Whatever half of this was, which was 2/3, that's what it factors into. And don't forget, that's a minus. So it's x minus 2/3 squared. Over here, you need a common denominator. So this is going to be 3/9. So it'll be 1/9. Ah, perfect squares. Nice. Square root both sides.
Well, that works really nicely because they have the same denominator.
Mm-hmm. And let's see. Now I have 2/3 plus or minus 1/3. Okay, so my answers are going to be, what color have I not used yet? Brown. So my answers are going to be.
The fitness gram pacer test is a multi-stage aerobic capacity test. Progressively gets more difficult.
Turn it off. I'm going to mute
The
everybody.
20-meter pacer test will begin in 30 seconds.
I don't know who that came from, but I'm going to remove you from the room. If you, hopefully it was just an accident.
I think it said Mike Max.
Who is Mike? I'm going to remove Mike. I don't know who Mike.
There's no Mike in our class.
There's no Mike in 8th grade.
Now, if you're Mike and you want to be in here, let me know who you are, and you're fine. You're not in trouble.
I don't think he's in geometry.
Okay, so we got to remove Mike. Mike's not speaking up.
Oh, whoever Mike is tried to get into science too.
Yeah,
And I think
he
history.
also tried to get into
Yeah,
history.
and also in the 8th grade Zoom night, and they succeeded. And also English.
Yeah, he got into English.
All right, it's okay.
One classmate
Maybe it's a kid on a
making
parent's
a joke.
computer, but
We should put out an Amber Alert and.
No.
wow.
Amber Alert.
Well, issue a warning to all individuals holding Zoom meetings.
To all Zooms.
Inform them that there's a potential. Inform them that.
Zoom bomber Mike.
It's still showing that.
I think we know they're an 8th grader.
It's still showing
Any
that
person with a name
Mike is
Mike to be
Because
immediately
unless
removed.
someone is leaking.
Maybe he's not removable.
Dang.
How can that be?
How would he get the invites or the numbers? And he has to be an 8th grader to get the updates from the peoples or whatever.
He has to be
Unless
able to.
someone's like leaking the Zoom.
It's not allowing me to remove.
He is the ultimate
He
hacker.
just overpowered the host.
I don't know. I do not know. I don't know what the purpose would be.
He's heck main.
Okay, I guess the attention. I don't know.
I mean, I don't think he's doing anything.
Yeah,
I don't think the fitness gram pacer test thing was him.
Let's get back to.
That was Mac.
Okay, let's get back to the math, please. 2 plus 1 is 3 over 3 is 1. Okay, 2/3 minus 1/3 is 1/3. So those are your two answers. Okay. Hopefully that didn't make us go late on this. Okay, any questions about this process?
Mr. Rosenthal, if like the answers to one of those parabola problems, both are area problems, and it requires a real answer, a real life answer, and both of them are positive, how do you know which one's correct or not?
You'd have to give me the exact problem so that we'd have the scenario to apply it to. One of them usually will make sense. Sometimes one of them is at the origin when something was on the ground, and sometimes the other one is away from the origin. So that's the second time that it hits the ground.
Okay.
You can clearly see which
just
one.
say it's both of them.
Yeah, both times they're on the ground, but it's, one was at the beginning and one was later on in time. It's with respect to time, sometimes you know which one you're talking about. Prior to a launch, if I start on a launch pad, I'm above ground. So where it would have hit the ground would have been back in time if you follow the pathway. Okay, I don't know if you can visualize that. But anyway, one thing, I want to show you one more thing here. And don't shout anything, anybody, if you know what it is. Let's start with this. Now try to follow along. And now we'll complete the square. And I know some of you already know what's going to happen here, and some of you don't.
Quadratic
Oh,
equation.
I said don't shout it out. Okay. Okay, now look here. We don't want anything there. So we divide everything by A. And we get this. Okay, I'm going to run out of space if I'm not careful. Okay, we get rid of this. We then cut this in half, so that's B over 2A, and then we square it. Okay, and that's what we add. So we add B squared over 4A squared on both sides. I'm going to add it here. This can now be factored into whatever half of that was, which was B over 2A. So it's X plus B over 2A squared. Over on this side, I'm going to get a common denominator. I can make A into a 4A squared by multiplying by 4A on both top and bottom. So on the top, now that I have a common denominator of 4A squared, I just get B squared minus 4AC all over 4A squared. Next, square root both sides. So then this will be plus or minus the square root. And the square root of the denominator is actually just 2A. Subtract B over 2A on both sides. And you can write it all over one denominator. And there's your quadratic equation that you get by just completing the square of your quadratic in standard form.
For a general case, you can derive a formula by completing it for a general case.
So if you guys can do this, then you can do all the rest of your completing the square problems. So this might be something to work on at home. Can you derive this? If you can derive this, you can do all the completing the square problems, and it's a good thing to know to strengthen your knowledge of all of this, the material that we're working on prior to taking the test, not after.
How does the denominator on the right side turn into 2A?
Give me a color.
How does,
here?
yeah.
How did I get from blue to pink? How did I get this to this?
On the right side.
On the left side, I'm asking you. I'm asking a question to answer your question. How did I get from
It's a quadratic formula.
Hold on, shh. How did I get from this blue to this pink?
Square root.
Ah, so I had to square root the right side, right?
Yes.
So you see that showing up here. What's the square root of 4?
2. Oh, okay. I see.
What's the square root of A squared? A, right? Okay.
David, why have you done this?
Okay, now we're going to go back to the lesson. Okay. We're going to run out of time. Okay, now finally, this is the purpose of doing this. Vertex form. Vertex form is helpful for finding the location of the maximum or minimum point. Those are very important points of interest. In calculus, those will be important points of interest, the max and minimum points. And those are where the vertex is. So when you have it in the vertex form, which you're looking at there, y equals a times x minus h quantity squared plus k, where h and k is the location of the vertex. So if you're able to get it into vertex form, then you know where the vertex is. It's an alternative way of locating the vertex. So let's write this one in vertex form. So the purpose of completing the square is to be able to rewrite equations in vertex form. Start working on this. rewrite this one in vertex form. Now you're going to learn how to rewrite the equation in vertex form using what we just learned. See if you can put that together. Okay. I would try to complete the square. Don't make this a 0. Do not make it a 0. You're going to have to use another trick other than adding something to both sides. What's the other way to account for something? Instead of adding. What?
Well, I said factor it out. That doesn't make sense.
No. Listen. Normally, if this was 0, I would subtract 22 on both sides. Now what I'm going to do is I'm going to bump it over.
You could also use derivatives to find the vertex coordinates for x and y. Then you could just turn it into vertex form regularly.
You can. Okay, that's going another route. All the routes are important to know. I'm going to bump the 22 over. I'm going to complete the square. How do I do that? Half of 10 is 5. Square it. Add 25. I don't want to add 25 to the other side. What is another way I can account for adding 25?
Plus 25 minus 2.
Minus 2?
Yeah.
3?
Then I've added 23 in value. Then I will have added 23
Yeah, minus 3.
I don't want to add 23 to one side and not to the other. It'll be out of balance.
No, what I'm saying is you have x squared minus 10x plus 25. Just make it so that plus 22 is the same as plus 20. So ignore the 25 that you put there and say plus 22 is the same as plus 25 minus 3.
Oh, yes, that is one way to look at it. Okay, that's fine. But here's an easier way for everybody to understand it. What was in green was already there. What's in pink was added to it. You can't just add without accounting. We're not adding on the other side. So what I can do is I can take away on the same side. If I'm adding 25 and subtracting 25 on the same side, I'm essentially adding 0, which is another identity. Over here, I can now factor this. Watch how this works out so nicely. This is now what was half of that was 5. So this is x minus 5 squared. And what's 22 minus 25? Minus 3. A is 1. H is 5. K is 3. My vertex is at 5, negative 3. I've located my vertex.
Wow.
This is now in vertex form.
Why is it a positive 5?
Because of what we talked about here. The form is, it's change in x, right? This is change in x.
Yeah.
Oh, Mike's
Also, it's minus. Okay.
Yeah, the formula is y is equal to a, x minus whatever the h is, plus whatever the k is.
Apparently there's 3 mics now, and then also a Mike Oak Small. There's also not an Oak Small in our class.
There's
No,
4. Actually,
there's
5.
4 mics.
No,
4
you
mics and
guys,
The
one.
fitness screen pacer test is a multi-stage aerobic capacity test that progressively gets more difficult.
Yeah, who's doing that one?
Now
30
it's
seconds. Line up at the start. The running speed starts
Okay,
slowly.
I'm gonna have to
And
contact
after you
somebody
hear
from
this
the
signal,
company because this is
a single lap.
not really funny. Okay, it's ruining what we're doing. I know that whoever's doing it is getting a lot of fun out of it, but it really is at the expense of everybody and what we're trying to do here. Okay. Now, if anybody happens to know who is doing that, please share that with me. And then that person is, if it is somebody from our school site, which is a possibility, we're going to have a major conversation with their parents and that student. And I'm very disappointed in whoever's doing that, okay? Because this is other people's time. All right, I know it's for a laugh, but it's very forceful. You're forcing yourself upon other people. Okay, I just want you to know
Mr.
it's immoral what you're
Oh,
doing.
they're back. Mr. Rosenthal, it seems as though the 4 mics have gone quiet.
Well, I mean, if somebody does find out, please, you can secretly message me if you know who it was, and that person will have to face the consequences. And that's just about all we're going to do. Now, Ms. Fontalea talked about this yesterday in our meeting. So Mr. Lauchu is aware, and they're already starting to take actions with Zoom to figure this out, all right, if it's going to persist. So I would recommend that the person just stop now while you got away with it, so be done with it. We get it. I totally get the humor in it too. I understand how that is funny. Just stop now. It's done. Okay, you're just slowing us all down with what we're trying to accomplish. All right.
Wait, how is it funny? That's not even funny.
But
It's
guys,
just
you
waste
might
of
not
time.
understand the
It's a
humor.
little bit.
Of course, someone doesn't get it.
Yeah, it's just not appropriate for what we're
Stern,
trying
you
to
don't like sliced bread.
How
I
do you
don't
get
get it.
all 4 microphones to talk at the same time?
Okay, folks, listen.
It is the same
All the same
person, just
person.
using
Folks,
different devices.
Folks, listen, we almost finished, right? We got really close. So there's probably going to be 2 homework assignments tomorrow, maybe. All right, you're welcome to do the evens from this lesson if you would like. Okay, but we are going to finish the lesson tomorrow. We are in office hours now. Thank you so much.
All right, thank you,
Thank
Mr.
you.
Rosenthal.
Okay.
Have a good day. Wait, sir and David, we have an English meeting, right?
Yeah.
Okay,
Why? Why so many meetings?
just let's go. Okay.
Mr. Rosenthal, I'll show you tomorrow, okay?
I messaged
We'll see
you
you
who I'm
tomorrow.
pretty sure it is because I heard his voice.
Mr. Rosenthal, I'll show you
Well,
tomorrow,
still
okay?
speculation.
All right,
Yeah, I
thank you.
know, but it's better than nothing. I heard his voice, and it was an 8th grader. So I'm not totally sure, but it's pretty sure. I would bet my money on it.
All right, well, then hopefully that person stops. Otherwise, we can maybe contact, okay? Next time, message me in Schoology so that people looking at this later don't know who outed them, or unless you don't mind them knowing that you outed them.
Okay, thank you, Mr. Rosenthal. Bye.
All right, bye.
Bye, thanks.
You got it. Thank you.
Okay, Mr. Rosenthal, I'll show you the points
Bye.
tomorrow, okay? See how they interact. All right. Bye.
Wait, say that again,
I'll
David?
show you the points tomorrow.
Okay, that's fine.
Or you can do it yourself. All right. Bye.
All right, bye. Thank you.
Thank you, Mr. Rosenthal. Have a good day. See you.
Okay, you too. Anybody else? Questions?
Mr. Rosenthal,
Yes.
do you plan on teaching down to the last instructional day?
Yeah, June 3rd and 4th, we're not going to have class. I forgot to announce that. Remind me tomorrow. Cut me off tomorrow and say, remind everybody we don't have class those days because everybody's going in to clear out their stuff, and I'm going to the school site to help from the early morning throughout the day.
Okay, thank you.
Yeah. Anybody else? Questions? Boaz, Lauren, Russell, Sophia. No? Are you there? Show me that you're there. Anyway, either chat that you're there or verbally say, I'm here. Or else I think you're away from your computer. Russell, are you there? Boaz, are you there? Lauren, are you there? Sophia, are you there? Oh, you raised your hand. I see. Okay. Why don't you just chat? I'm here. All right, I'm going to end the session. I'll see you tomorrow.